Hi everyone, my name is Renan Guarese. I'm a PhD student at RMIT University in Human-Computer Interaction. And today I'm going to present a work I've done with some former colleagues as part of my master's dissertation at UFRGS here in Brazil. The paper is called Augmented Situated Visualization for Spatial and Context-Aware Decision Making. So as an introduction, I'm going to start talking about data visualization in a map context. It's usual to have maps in larger scales, such as these three here, where you can see whole country with data from different states, or a whole state with data from different cities inside that state, or even from a city with data from different streets or neighborhoods. This here on the right is a traffic data visualization, and these ones on the left are for COVID cases. And we're by now very used and maybe even tired of seeing these. So we can also do the same thing in a smaller scale. Here on the left, you can see a building evacuation plan. So you can have data being shown inside the floor building map, such as the best paths to evacuate it in an emergency, or where the fire extinguishers or hoses are. Here on the right, there's a bathroom floor plan where you can see data placed in a map for a small bathroom, like the positions of and distances between appliances, and also where the plumbing and electrical wiring is done. So it's possible to do these same types of visualization in these smaller scales with augmented reality. And this is what I'm going to talk about today, situated visualization in augmented reality. Most of my work was done related to this area, and the one I'm presenting today is about decision making in a seat choosing task. We'll be analyzing data from physical classrooms in my former university. Okay, so the main motivation and objectives for this was to explore ASV, this augmented situated visualization, as a concept, to expose the effect of ASV on decision making whenever it's compared to traditional 2D map visualizations, and to design and implement an interactive visualization of seat data in a classroom in order to help people to choose seats for them to sit at. Regarding data visualization and augmented reality, there are several works that are not situated in the user's local context. They're just displaying data wherever in the surrounding space of the user. There's no actual reason for the data to be exactly there where it's being seen. In this case, on the top right here, we can see molecular particles, and they're just laying around in the environment, like in a proper spatial context. Some other works are more focused on conceptual definitions, coming up with different terminologies and how these concepts might affect the user experience in data visualization. However, these usually don't expose any user tests to support those claims, usually not implementing anything since they're more theoretical works. Finally, there are some few application papers where researchers test actual interfaces for situated vis in augmented reality. In this case here, on the bottom right, there was a product visualization in a market environment where you could see nutritional data facts about different products. In this particular case, there was a user study, but it wasn't that thorough, and the comparison was just between their implementation and actually reading the box, which some might say isn't exactly fair, since the data wasn't exposed in the same format as their AR version. Okay, so for our set of user tests here, we're going to present both an augmented reality visualization and also a 2D map visualization. This 2D version of our classroom was done solely for comparing the two of them in as fair of a comparison as we could. So you can see the same data with the same elements, but in different visualization paradigms. In this first view on the top, users would see a visualization for airflow in a classroom. So if you wanted to sit closer to where the wind is blowing, for instance, you could analyze the data there, which is even more relevant now, I think, because of COVID. The next one on the middle here is for the circulation of people. The idea is if you wanted to see where the minimum amount of people might be walking in front of you during the presentation, or in case you have mobility impairments and can't be standing up all the time to let people pass by you, you could check the data here to choose a seat. And this last one is for special seats. So in case you're looking for a seat with a hearing aid or an extra wide seat or a left-handed desk, for instance, you could look at this data set. These are just 3 examples out of some we managed to come up with. All of the data sets were made up of fabricated information in order to have multiple pieces of data to compare with the users and alleviate any biases. However, all of them could be actually measured with either sensors or previous knowledge of the room. Considering the interaction aspects of the project, on our AR approach, we use a hand-guided virtual menu. So whenever you would look at your own hand, you'd see a menu hologram, and you could select one of those options or a combination of those, and the data would be filtered according to the selections. These selections were done by gazing or centering your vision at the desired option and doing an air tap gesture. A similar interactive menu was done on the tablet for the 2D map version, which was just a simple 2D menu here on the left. Okay, so I'm gonna present a video here. Of the application running. Here the data is being displayed in AR in an egocentric perspective using the Microsoft HoloLens as a headset. So the user would see and interact with all of this in first person. Okay. So it's just a small demonstration, sorry. Going over now into our user study design, we separated the attributes that could be chosen into these 3 nominal categories: scalar scores, vector routes, and categorical scores. Then we divided these categories into a series of tasks for people to perform. There were 6 different tasks for each user under each of the 2 platforms. The tasks would scale in complexity following the dual process theory of cognitive science, where tasks of type 1 are the most straightforward and easy to perform, and type 2 were the more complex and the ones that demanded more of an analysis of the data. So we would only use one of the attributes per task in the tasks of type 1, and in all of the tests of type 2, you would have to analyze a combination of those attributes in order to make it more difficult to choose a seat. So in task 6, for example, the most complex one, the user could be asked to choose a seat with the highest temperature, where there would be the least amount of people circulation, and there would be closer to a power outlet. None of the attributes is repeated in the same platform for a single user in order to avoid learning bias. The order of the attributes in each category was sorted among subjects to minimize any pattern repetitions. 2 different data sets were used for each attribute as to minimize learning bias across platforms. Both the data sets and the platforms tested were alternated using a Latin square among the participants to again avoid pattern repetitions. Getting now to the results, we had 16 subjects participating in our trials. 7 were female and 9 male. All of them claimed to regularly use touchscreen devices, and only 3 people said they use some augmented reality head-mounted display at least once a week. Given this difference here, in order to minimize previous knowledge bias, we made a short tutorial for people to get familiarized with the HoloLens. Regarding now the objective results in our tests, one of the things that we measured was the amount of walking steps people took around the room. And here you can see that the tasks with the HoloLens demanded 13.5% less walking steps. And this was a statistically significant result. You can compare this here. The blue curve is for the tablet version, and the red one is for the HoloLens. Also, down here in the accuracy of the choices people made for the seats, users had an average of about 4% higher accuracy using the augmented reality approach when compared to the 2D one. But this was not statistically significant. Over to the subjective results, the 2D maps did get better scores for all 3 of the attributes that we measured, usability, simulation sickness, and workload. However, at the same time, the ASV approach did score acceptable marks in all of these. Regarding the presented results, we can see that since screen-based visualizations are more commonly used, they can be considered a gold standard for this sort of task. Although we had acceptable subjective results, the AR visualization still felt more like a foreign concept to most of the users, given the novelty aspect of the technology. Regardless of all of these points, our approach still surpassed the 2D visualization in most of the user performance aspects measured, such as the walking steps and the choice accuracy. Finally, we can summarize the work with some points here. Our study served to showcase augmented situated visualization in a decision-making context, following different sets of user-centered criteria. The use case application we implemented objectively helped users choose seats on a classroom environment based on sets of spatially situated data provided to them in AR. ASV overall had comparable results to a well-established visualization paradigm, that is 2D maps, including even some results in its favor. And now the next effort in this project would be to evaluate a similar visualization in larger environments, such as a theater or an auditorium. The idea here would be to extract more significant perceptual results from the users, since the impact of situated data is likely to have a greater impact on more sparse and broad environments. Okay, so that was it for today's presentation. Thank you all for joining me, and I'll be here to answer any questions.